Now we're going to start talking about operationalizing data. And specifically in this lesson, we're going to talk about creating new variables within a data step, and we'll also talk about expressions and functions in that context. What do I mean about when I say operationalizing the data? Well, this again is just a reminder of our overall data flow, starting from raw data down to SAS data sets, where you may merge them together into one data set, at which point you might stack multiple data sets together, or continue to operationalize by subsetting, or in the case of this lesson, by actually operationalizing some of the variables in your data set. For example, if you ask a dietary questionnaire, you may have a couple hundred questions that you want to operationalize down into, say, 2 or 3 variables that somehow represent nutrient intake or dietary pattern for your analysis. Other common examples in epidemiology would be smoking questionnaires, where you ask many questions about whether or not the participant smokes, and if so, when they started and possibly when they stopped, how many cigarettes per day, did they smoke other forms of tobacco, and on and on and on. And you need to take all this information for your analysis and somehow boil it down, distill it down into some key variable or key set of variables that represents the underlying construct that you want to represent in your analysis. So that's what I'm referring to when I talk about operationalizing the data. It's essentially taking the data and creating the actual variables that will be used in your analysis based on the raw data collection in your data set. And this tends to happen in this stage where you're refining and modifying data sets prior to the analysis. So the core objectives here are to help you understand how to create new variables in a data step. I want you to understand how to use mathematical expressions within a data step and understand how SAS functions work. So one of the first things you should do before we move forward is just pause and take a moment and make sure you have your editor file open and that you're very clear now on how to merge together data sets by a unique identifier and how to get only participants into your data set that are common to all of the data sets, and how to include or subset your data according to characteristics of these participants. I've given some characteristics down below, 20 years or older, with systolic blood pressure values that are not missing and they're also not equal to 888, and those same conditions apply for the diastolic blood pressure variable. So take a minute and get that ready, and then we can move forward again, and I'll go through some examples in the slides talking about variable creation, and then we'll go to SAS and see how that looks in the actual editor file. So just as a reminder, with data steps, since you just got done creating that SAS data set, again, it always starts with the data statement, followed by the name of your new SAS data set and the location. Then it would be followed by some statement which identifies where the input data set or data sets are coming from. In the previous example, you would be using a merge statement to specify to SAS which data sets you want to merge together, and then it ends with the run statement. Now, in between the data statement at the beginning and then the merge or set statements, and then at the end the run statement, in between those those various pieces of information is where you operationalize data and create variables. So variables are created and redefined in a SAS data step using assignment statements. And the basic form of those assignment statements is that you have the variable name, which is user defined, on the left. So you will have to come up with a name and type it out. Then you add an equal sign, and then you'll have some sort of expression that tells SAS what kind of information do you want this new variable to hold. And these assignment statements will always end with a semicolon. Okay, so this is what it would look like in its basic form, and again, this will be held within the body of a data step. Now here's a generic example where we're going to use a mathematical expression to create a new variable in a data step. And in this particular example, the data step contains a set statement, so we're not merging together data sets, we're just refining one standalone SAS data set. Now in this example, we're naming the new SAS data set as a temporary data set in the work data library, and the name given is just new data set. And we're starting hypothetically from a data set that's located in this data library named existing data set. And the new variable being created is named LDL-CHOL, short for LDL cholesterol. And that is being created simply by typing in the name of the new variable we wanted here. So I actually had to come up with the name and type that out. Then we specify an equal sign. And here we have an expression that's giving SAS information about how to populate this variable with the information we want it to have. And the information that we want is, in this example, we want a mathematical expression that looks at the value of total cholesterol for each participant, subtracts off the value for HDL cholesterol, and then subtracts off triglycerides divided by 5. This is just LDL calculated based on the Friedewald equation. And the key point about this particular assignment statement is that total CHOL, HDL CHOL, and TG are all variables that had to exist in the input data set. In other words, these three variables already have to exist in libref.existingDataset because the calculation is dependent on values for those variables. And the 5 here is just a constant. So that's not a variable, but SAS views it as a number, and it's actually taking the value of triglycerides and dividing by 5. If TG, HDL chol, and total chol do not exist in the SAS dataset, in this input dataset, you'll get an error in the log. It will probably say something like, these variables have not been initialized. That simply means they're not in the dataset, therefore we can't create this new variable, LDL chol, because we don't have the input information from these variables. And you can go on within the context of a data step and create as many new variables as you like. And when you're done, you would add a run statement, then you could highlight and submit this to SAS, and you would end up with a new SAS data set that now contains not only the original 3 variables, but this 4th LDL-CHOL variable. So remember that the left side of the equal sign in an assignment statement specifies the new variables being created. In this example, it was LDL-CHOL, user-defined. And the right side uses a mathematical expression. And it creates the mathematical expression based on existing variables. And in this example, those 3 existing variables were total CHOL, HDL CHOL, and TG. As I mentioned before, multiple variables can be created in the same data step, and this simply demonstrates an example of that. So again, this is a hypothetical data step. We're creating or naming our new SAS data set here in the data statement. We're identifying the input data set here in our set statement. And then we have a series of 5 new assignment statements that create 5 new variables. Here again is the LDL chol variable that we just talked about in the previous slide. Next, I'm creating a weight change variable. Weight CHG is the actual variable name, and that is defined by the difference between end weight and start weight. So you imagine that your input data set has a variable named end weight and a variable named start weight, and you're simply taking the difference between those two variables to arrive at a value for weight change. The next variable is meant to represent percent weight change. PERWTCHG is the actual variable name, and that's equal to the difference between values of end weight and start weight divided by start weight and then multiplied by a constant, 100. And the final two examples are two different ways of creating BMI. So BMI is defined as weight in kilograms divided by height in meters squared. And I'm creating that variable first in the first example here by defining a new variable simply named BMI and setting it equal to the value for the weight variable divided by the product of the values for the height variable. So in order to get the squaring, I'm simply multiplying height by itself in the denominator. Now again, weight and height are variables that have to exist in your data set, and obviously they have to be in the correct units. It's an easy thing to overlook, but if weight comes in pounds and height comes in feet or inches, you'll have to make the correct conversions, also using assignment statements, before you can create your final BMI variable. Here's an alternate example of BMI where we're simply taking weight divided by height squared, and the double asterisk is the symbolic representation for SAS of exponentiation. So if you wanted to raise something to the fourth power, you'd just have the double asterisk and the number 4, etc. These two variables, BMI and BMI alt, are identical. They're simply being created in different ways, and that's a very common thing you'll see in SAS, is that the coding is fairly flexible and there are often multiple ways to achieve the very same outcome. Then finally you'd have a run statement, and now your new output SAS dataset, work.newDataset, is going to contain all of the original variables that were in the input dataset, existing dataset, in addition to 5 new variables that you've defined here on the left-hand side of each equal sign. This is a quick overview of different types of expressions that can be used within a data step. So on the left in this table we have the type of expression, and then on the right is a sample assignment statement. For example, if you wanted to create a variable that held a numeric constant, you could do that. So the example here creates a new variable that's called norm BP, and it's simply being set equal to a value of 120. If you were to put this within a data step, the body of a data step, and then run a proc print, for example, and look at values of norm BP, you'll see every participant or observation in your new data set will have a variable norm BP, and it will have a value of 120 for that variable. Similarly, you can create character constants. In this example, we're creating a variable called gender, and we're setting it equal to male. If you create character constants, or anytime you work with character variables in SAS, the actual characters need to appear in quotation marks. So in this example, your new output data set will have a variable gender, and everyone will have the exact same value, which is male. So obviously you want to be careful about setting numeric constants. There has to be a reason for doing so, so that it makes sense within the context of your analysis. If you wanted to rename a variable, you could do it as simply as creating the new variable name on the left-hand side of the equal sign and specifying the name of the old variable on the right. Now in this example, if there were a variable named BMI old in your input data set, you could create a new variable that would appear in the output data set named BMI new. It would have the exact same values as BMI old, and unless you told SAS explicitly to get rid of the BMI old variable, your new output data set would contain both the old and the new variables. That's not always very efficient if you have no need for duplicate variables, so another way to rename variables using assignment statements is to combine an assignment statement with the rename statement. So quite simply, you you would just type out the word rename. This is a SAS statement, so SAS gives special meaning to this. And then you would follow it by this syntax, old name equal new name. And if we wanted to use the BMI example from above, that naming convention, then we would simply say BMI old equal BMI new. And your new output SAS data set would only contain one BMI variable, the BMI new. And the BMI old no longer exists because it's literally been renamed in this particular setting. So note that this is one exception to the general approach where the new variable name is on the left-hand side of the equals sign. And then here are some additional mathematical expressions, the final four. Basic examples of addition, subtraction, division, and exponentiation. And I just want to clarify again and remind you that if you want to raise something to a power, you simply connect the variable and the power to which that variable should be raised using a double asterisk. Now let's talk about SAS functions. A SAS function performs a calculation on or some sort of transformation of arguments that are given to the function in parentheses following that function name. That's a mouthful, so let's take a look at some actual sample code in the slides here. So again, here we're working in this generic example where we're creating a new output SAS data set. It's temporary, it's named new data set. We're starting from a permanent SAS data set in the LibRef library named existing data set. And the syntax again starts by naming the new variable on the left-hand side of an equals sign. Specify your equals. Then you give the function name and in parentheses some arguments, semicolon. And that will run your function. There are many functions available in SAS, and you can go to the online help to browse through and take a look at various functions that may be appropriate for your research. I'll provide a few examples when we go over into the next few slides and then into the SAS editor files. One thing to note here is that the arguments in parentheses quite often are existing variables in a SAS data set. So usually you want to create a new variable based on some transformation or a rearrangement of existing variables, and they often make up the argument or the arguments to the function. Each function has a different, slightly different approaches to specifying the arguments, which is why it's important to read the SAS help for any particular argument you want to use. But I'll give a few examples of some commonly used functions here. In this example, within the body of our data step, you can use the mean function to create mean blood pressure. I'm creating an actual variable name here that is mean BP. And I'm setting that equal to this function. So I use the word mean because that's the actual name of the SAS function. SAS gives this meaning, and it will be highlighted in blue or in some color within the body of your data step when you put this in an enhanced editor file. And then in parentheses you need to specify the arguments of the function. And what the mean does, as you would expect, is it simply calculates the averages across values for multiple variables. Quite often in epidemiological studies, if you're studying blood pressure, you'll take multiple blood pressures, and you might then want to analyze the average of all of those blood pressures, or maybe the average of the last two, depending on the method you're using. In this example, I'm assuming that there are 4 blood pressure variables named SBP1, SBP2, SBP3, and SBP4, and I'm specifying those as the arguments to the mean function, and note that the variable names need to be separated by commas. Then they're enclosed in parentheses, and there's a semicolon, and now I'll have a new variable in my output data set named mean BP, which will contain the mean of all these values. You could compare this below to this second variable, which I named mean BP alt, which simply uses a mathematical expression. It takes the average by first calculating the sum and then dividing by the number of values in the numerator. So this is an alternate way of doing it. It can be a little more cumbersome if there are a lot of arguments that you want to take the average of. For example, if you have 20 variables and you want the average, this can be a little bit more problematic and more error prone, but either way you do need to type out all the variable names. In this example you also have to count them up and make sure you get the denominator right, whereas with the mean function you don't need to do that. Another important difference is that when using the mathematical expression in the example of mean BP alt, if any of the variables that are being provided to the function as an argument, if any of those variables have missing values, the value for the new variable, mean BP alt in this example, is also going to be missing. So you need to be sure that you have values for all variables in the argument. Or, at minimum, you need to be sure that if any one of these is missing, you want the final variable to also be missing. In some situations that may be desired, and in other situations you might be happy if, as long as one of these variables has values, you want to get some sort of value for mean BP alt. In that context, then you would want to use the mean function up above, because the mean function will take the mean based on any values that are present in the argument specified, as long as at least one variable or one argument has a value. Okay. So you'll get different answers using these two different approaches, and it's based on the missingness patterns for the variables that serve as arguments to the function. Now again, SBP 1, 2, 3, and 4 are all existing variables in the input data set, and you're using those to create new variables. In one example, mean BP, and in the second example, mean BP alt. I'll let you read through those additional notes, and we'll move on to a couple other useful functions. Here's an example of the sum function. I'm creating a new variable in SAS named total alcohol, which is equal to the sum of beer, wine, and liquor. The assumption here is that beer, wine, and liquor are actual variables in the SAS data set, and what they represent is maybe grams of each kind of alcohol consumed in the last 30 days or on a weekly basis, however your questionnaire is structured. And the sum function will quite simply just take the sum of these three values, the values held by these three variables, and it will put that value into the new variable total alcohol. In the next example, we're doing a log transformation, so I'm creating a new variable named WBC log. I'm using the log base 10 of the variable WBC. WBC has to be an existing variable in the input data set, in other words, an old data set. And then by using the log10 function, I will get the log base 10 of the value for WBC, and that will be held by the new variable WBC log. The round function is another useful thing. Here I'm creating a variable called BMIR, which is equal to the original BMI variable rounded to the ones place. So you just use the round function, and then the arguments to that would be the variable and some information about how you want the variable rounded. And in this example, by placing a 1 in this place after the comma, you're telling SAS, round this BMI variable to the nearest 1. And here I'm just reiterating the point that you can put multiple assignment statements and use multiple functions within one data step. So this just brings it all together. So now why don't you go ahead and pause the lecture and go into the SAS editor file, and in the new data set that you created, try to create a new variable named BMI by dividing weight in kilograms by height in meters squared. and also create a new variable named pulse pressure simply by taking the difference between systolic and diastolic blood pressure. Now, one thing to be aware of is in the input data sets that you have for this class, the height is given to you in centimeters, so you'll first need to convert that to meters before you enter it into your BMI calculation. So go ahead, give that a shot, and then come back in and we'll go look through the editor file together and see some of these examples in real time. Okay, so we're back and going into SAS. I have an editor file already open. This is lesson 7. And all of this we've been through before, so these initial sorts I'm just going to highlight and submit. Seen that, and we know what that's about. All seems to work. Now before I actually run the data step, I'm just going to walk through and remind you of a few things. So again, the data step starts with a data statement where we name our new output data set. Then we have to tell SAS what existing data should be used to generate the new output data set. So there are 4 SAS data sets we've been merging together. We want to merge them by ID number. And then I'm using an if statement to subset this data set. And specifically, I only want to include individuals who are common to all 4 data sets, who have an age greater than equal to 20, who don't have a systolic blood pressure equal to 888, who don't have missing systolic blood pressures, and also for diastolic blood pressures, I want to remove the 888s and individuals with missing. Right, so here I create a BMI variable based on height and weight. And as I said, the heights are in centimeters, so first we need to convert from centimeters into meters. And I do that by creating a new variable that I'm naming height m here in line 43. And that is equal to the original value of height in the data set divided by 100. And now I can move forward and create the BMI variable. So I name my new variable BMI, and that is equal to weight divided by height m squared. Now again, I need to specify the new height in meters variable which was created here. And this is an important point about how data steps run. You can't use a variable within a data step until it's been created. In other words, I couldn't move this BMI calculation up to line 42 and then convert height in centimeters to height in meters, because I need the height in meters variable to create BMI. Some softwares can look through the whole data step essentially ahead of time, and they'll see that you're going to create the variable, and they'll create that first and then come back up and make your BMI variable. But SAS is more linear, and you need to create all variables that are going to be used in later calculations earlier in the data step. And then here I just give an alternate approach to creating BMI. So instead of creating a separate variable for height in meters, I simply divided height by 100 using the appropriate set of parenthetical references in the denominator to end up with a new variable called BMI2. And BMI2 should have values identical to BMI defined up in line 45. Then BMI3, in this example I'm taking weight divided by height m times height m. Again, give us the exact same output, it's just a slightly different way of going about it. Here I've given a very simple addition example. I'm creating a variable called SBP2, and that's equal to the value of SBP plus 2. Again, SBP, it has to be a variable that exists in the input SAS dataset, and your output SAS dataset then will contain both SBP2 and SBP. Similar approach for DBP2. Here I'm creating some constants as we saw on the slides. Constant 10, so there'll be a new variable in the data set named constant 10, and all observations will have a value of 10. Here's the pulse pressure variable that we talked about as a part of the exercise. So you simply typed out the word pulse pressure and set it equal to SPP minus DPP. Here's an example of using a rename statement. I'm renaming the existing variable subscap SF, which is subscapular skin fold. I'm renaming that to SSSF. Here's an example of the mean function. The new variable mean BP will simply represent the average of systolic and diastolic blood pressure. Here are a set of log transformations, log base 10 and natural log. And in this example, in line 77 that I just highlighted, this is simply an example of using the log function, and instead of taking the log of just the value of a particular variable, I'm putting a broader argument in here. I'm saying take the log of the BMI value plus 1. And this is often useful if you may have tests that often have zeros. So maybe with laboratory tests, undetectable levels get a value of 0, and you want to somehow represent those in the analysis, you might want to add on some small constant so that you get a value for your new outcome variable. And here are some examples of rounding. BMI R1 rounds to the ones place. Here I'm rounding to the tenths place. And you see I have a 0.1 specifying that rounding as a part of the argument. The next variable rounds to the hundredths place, so I've specified 0.01, and the next variable will be BMI rounded to the tens place, and that's specified by the value of 10. Now I'm going to highlight and submit this data step, and then I'll also highlight and submit this proc means and proc freq, and we can take a look at some of the new variables that were created in the SAS data set. And also note that in this proc freq, to demonstrate the BMI rounding in a more manageable way, I'm using the obs equal option to the data set, to the data equal option, to tell SAS only run this procedure on 20 observations. And that's just going to make the output a bit more manageable. I already ran the sorts, so I just need to highlight my data step. Submit. Then there was an error. So we'll take a look and work back and see where the error was. So it looks like the data sets merge because I have a message saying here that work.master has 12,733 observations and 30 variables. So everything seemed to work up there. The problem happened first in the proc means, and it's telling me file work.master1 does not exist. So this was an error on my part. It wasn't intentional, but it's a good learning opportunity actually. The problem is that I'm asking SAS to run the means procedure on a data set that doesn't exist, master1. What I intended to do was to have it run the means procedure on the data set work.master, which we created above. Okay. And then we get the same error for the proc freq where I'm specifying the wrong data set. And this happens very frequently when you're working with multiple data sets in multiple locations. So make sure you check the log file and you don't get any errors like that. And it's a simple fix. I just need to go back into the editor file and change these data set names to work.master. Now I can highlight it, submit that. There are no errors, and we have output. And this just shows the fact that several of the new variables you created based on other existing variables in the data set have real values and distributions, etc. And the variables were created correctly, and you get some basic descriptive statistics. Now if we look at the output In the proc-freq for the different BMI variables, you can simply see the effect of the rounding. So here, BMI 1, of course, everything's rounded to the ones place. BMI tenths, now all the values are rounded to the tenths place. And here's the example for the hundredths, and then here for the tens. So obviously this groups people together differently. When you round to the hundredths, there are no ties. So there's a frequency of one person who has a BMI value of exactly 17.22. There's exactly one person with the BMI of 17.79, etc. When you're rounding to the nearest tens, now everybody is grouped as having either a value of 20 or 30. There are 14 individuals with the value of 20 for BMI, and there are 6 individuals with the value of 30. So the rounding can be helpful, but you need to be careful to round it to an appropriate level of precision given your data. Yeah, so that concludes this lesson. And in summary, the main point here is that there are many different ways and approaches to creating new variables in SAS. They generally use, new variable creation will generally require a basic assignment statement of some sort, and SAS functions can be very useful. So again, I recommend that you look online with the SAS help or go to Google, type in SAS functions, and you should quickly get to a long list of various functions that can be used and find the functions that are most appropriate for what it is you need to do.